Hello everyone and welcome again to the new lecture. And now let's start quickly to the next example of the Lagrangian dynamics. We're going to calculate the Lagrangian and we'll do the equations of motion. So today example, I'll try to finish two examples, and one is very important, which is for double pendulum. So before that I'm going to do a simple one example that is very interesting, and this is uh, the question that is, if I have two masses which are connected like, say, this is my example, is if I have a table, and if this mass is connected with a string, if I have a hole here and this is connected with a string, a mass is connected with a string, this is, say, mass m1, and then this is hanging down, a second mass is hanging down. So this is, say, this is m and this is m, and say this is, so the constraint is that constraint. What is the constraint here in this problem? Constraint is that the mass m, which is this mass, the capital mass which is hanging down, is can only do vertical motion. Okay, vertical motion. So it cannot do like this, it can go up and down only. Okay, so this is the restriction. So this restrictions mean that if I have the total length of this is the total length is L, so then this is, if this is R, so this is going to be L minus R. Okay, this is what the constraint is there. So so if this is rotating, this small mass is rotating around it, so I have to write the Lagrangian and then find out the equations of motion, and we'll see that what is physics behind it. So naturally I'm going to work, because there's a rotation involved here, so I'm going to work in plane polar coordinates. So generalized coordinate in this case, generalized coordinates R, this is Q1 is going to be my R and Q2 is going to be my theta. These are the two generalized coordinates. So I'm going to have two equations of motions. So for that I had to write the kinetic energy first. So the kinetic energy, because this is half m, for this is going to be r dot square, because, and r square theta dot square. This we have already, this you have to remember, that whenever you're doing a plane polar coordinate, if the r is not constant, so the kinetic energy is always going for that mass is going to be r dot square plus r square theta dot square. If the r is constant, because in case of pendulum r is constant, you see you get r dot r is constant, so r dot is, that means L dot is 0, so you don't get, only get half m L square theta dot square. Okay, so not this r dot square factor. So anything which is in which your r is not constant, you are always going to have the kinetic energy half m r dot square r square theta dot square. And then for this mass, the second mass, this is half m, its coordinate is L minus r, so this is going to be L minus r dot square. Okay, this is restricted to only do this motion, so there is no angular concept here. So so now I can write this half m r dot square plus r square theta dot square plus half m, this is r dot square. So I can write as half m plus m r dot square plus half m r square theta dot square. So this is my kinetic energy. Okay, so this is okay, and then I can write the potential energy. Potential energy is V is, because this is the height. What is this? This is going to be minus mg L minus r. Okay, this is my potential energy. So sorry, this is capital M G L minus R. Okay, now I can write the Lagrangian here. So this is T minus V is going to be half M plus M. This is R dot square plus half M R square theta dot square, and this is plus MGL minus R. So once I have the Lagrangian, I can write the two equations of motion, which in terms of R and theta. So first equation is say Lagrange equation of motion, delta L by delta R dot minus delta L by delta R equal to 0. So let's calculate it first equation. So for that I had to calculate delta L by delta R dot. So delta L by delta R dot, if you calculate it, so R dot is one is here and there's nowhere else, so this is M plus M, this is going to be R dot. Now I can calculate delta L by delta R, this one delta L by delta R. So R is here also and here also, so I can have from here that is going to be M R theta dot square, and from here this is going to be, because R is here, so with the negative sign, this is mg, okay, minus mg, because mgll is not there, so minus mgr, so this is going to be mg. So once I have these two equations, I can put this into this equation to get the equation of motion. So I'm going to get is d dt of this, and this is going to be m plus m r dot and minus of this thing, so this is going to be minus mr theta dot square plus mg is equal to 0, or if I, this is going to be m plus m r double dot minus mr theta dot square plus mg equal to 0. Or you see that this is coming out very nicely. This is mr double dot equal to minus mg plus mr theta dot square. So you see that this is my first equation of motion. Now this is force which is acting, r double dot is the acceleration and the combined mass m1 and m2, and the two forces are acting. One is mg, you can see here mg with negative sign, and with the positive sign mr theta dot square. Mr theta dot square is nothing but the centrifugal force, because this mr theta dot square, this is mr theta dot is omega square, and this is v is equal to omega r, so this is nothing but mv square by r. Okay, so this is centrifugal force. So two forces are acting. One is mg on this is mg, and this centrifugal force which is acting on this this part. So if this is a spinning, this if this is a spinning fast, and this is this can do only this motion, then what is balancing the system as that is the force which is the moment if mr square centrifugal force which is taking outside, and this gravitational force with the opposite signs, this minus and plus, are balancing the system, and the system is keep on revolving. Now the second equation left is which depends upon theta. So this we can calculate, that is this is going to be d dt of delta L by delta theta dot minus delta L by delta theta is going to be 0, and my if I calculate this delta L by delta theta, so theta dot is here, so this is going to be m r square theta dot, so this is going to be delta L by delta theta dot is going to be m r square theta dot, and this delta L by delta theta is, so delta L by delta theta is 0, because there is no theta, not here, not here, not here, so there is no theta, so this is going to be 0. So now if I put these two equations here, so because one is 0, so I have d dt of this mr square theta dot is going to be 0. So now you see this is this is very well known equation, that because this quantity is nothing but angular momentum. So that is L equal to mvr. So this is going to, V is basically omega r, so m omega r with r, so this is going to be m omega r square, and omega is theta dot, so this is going to be mr square theta dot. So time rate of change of the angular momentum is 0. So angular momentum is conserved in this process. Okay, so one is spinning, and then this can do the this mass can do this vertical motion. So they are balancing, the centrifugal force and the gravitational force are balancing. This is from this equation, and the second equation is giving you that the angular momentum is a conserved quantity in this particular motion. So this example was nice example to, now you are able to write the Lagrangian. You are able to figure out what are the generalized coordinate, important generalized coordinate, and then depending upon generalized coordinate you can write the constant equations of motion, and from there you can derive some physical insight on that. Now let's move to the equation. This is known as the next example. I think let us take the next example, which is say, I think what example, the next example I have is with me is okay, so I have a simple pendulum. uh, you see that I have a pendulum. So, and what is the situation that this is my x-axis and this is my y-axis, this is my reference point. So the part where this pendulum is attached, okay, this is the pendulum is attached, where the pendulum is attached is moving with the constant velocity. Okay, so this part here is moving with the constant velocity, is moving here with this constant velocity. From t equal to 0 it is moving with constant velocity. So what I'm going to get is this simple as we do, and we have this is mass, and then I have x and y coordinate. So this is my this is my L sine theta, because this is my theta, and this is my L cos theta. Okay, we already figured out it. So I can remove this. So this is my L cos theta and L sine theta, and this is moving with the constant velocity along this. So this is going to have some x and y coordinate, and this is also going to have some coordinate, because it is moving. The coordinate is not fixed at the origin, so it is moving. So so what is x for this is going to be, x for this is going to be, say, some x naught plus my this one, this x direction, because from here, so this is L sine theta, and this x naught is what, this is, say, this x naught is the coordinate of this. Okay, so this is say this is x naught y naught, this position is x naught and y naught, but y naught is 0 because it is a reference point, is along the x-axis, so y naught is 0. So but y naught is 0 in this case. I just have x naught, and what is x naught? X naught is, will depend upon, because it's moving with a constant velocity, that is going to be vt. So this is going to be vt plus L sine theta, and I can find out this x dot is going to be v plus L cos theta and theta dot, and then I can write my y is nothing but this thing, this is minus L cos theta. So I can write y dot as L sine theta and theta dot. So now once I have x dot and y dot, which are my coordinates, and so I can write my and kinetic energy T is, this is half m x dot square plus y dot square. Okay, so this is mass of the ball. So this is half, say, m, so I have v plus L cos theta dot the square of this thing, and this plus y dot, this is L sine theta theta dot square. Okay, so what I'm going to get is half m, and then v square plus L square cos square theta theta dot square, and then you have twice VL cos theta theta dot square, and this term is L square sin square theta theta dot. So this L square cos square theta theta dot L square sin square theta dot is going to give me L square theta dot square and this V square. So my T is half m, this is going to be L square theta dot square from these two, and then I have V square, and then the third term is twice VL cos theta theta dot. Okay, so this is my kinetic energy, and the potential energy is going to be same. This is going to be minus mgl cos theta, because this is the height, this is the height, and this is below y-axis, so this is going to be negative mgl cos theta. So now I can write my Lagrangian is t minus v is, always write Lagrangian, because when you are going to differentiate it, you can do a little mistake, as I did in my previous lecture. So this is going to be L square theta dot square plus V square plus 2VL cos theta theta dot, and this is going to be plus mgl cos theta. So now I'm going to again have, because only the generalized coordinate is theta, because L is constant here, so I'm going to have only one equations of motion, that is going to have d dt of delta L by delta theta dot minus delta L by delta theta is going to be 0. So I have to find out this delta L by delta theta. So delta L by delta theta here in this case is theta dot is here and theta dot is here. So this is going to be ml square theta dot, and from here I'm going to get, because 2 will cancel out, so I'm going to have this mvl cos theta. Okay, so this is going to be del L by del theta. Now I have to find del L by del theta. So this let me write delta L by delta theta dot is ml square theta dot. This is ml square theta dot plus mvl cos theta, mvl cos theta. Now I have to find delta L by delta theta. So delta L by delta theta, you see the Lagrangian. So theta is coming here, so I have twice VL minus sine theta. So this is going to be minus twice VL sine theta. First term is minus twice VL sine theta. Twice will not be there because m will cancel out, and I'm going to have mvl sine theta, because m is here, so 2 will cancel out, so I have mvl sine theta theta dot, mvl sine theta theta dot, and the second term is the cos theta is here, so this is going to be minus mgl sine theta. This is going to be minus mgl sine theta. So now once I have these two equations, so I can write Lagrange equation taking the time derivative of theta dot with respect to theta dot, and then subtracting to this. So I had to get this d dt of delta L delta theta dot. So what I'm going to have d dt of this one, this is ml square theta dot plus mvl cos theta. So I'm going to get is ml square theta double dot plus, because v is also constant, is moving with the constant velocity, it's not going to be affected by time, so only cos theta will be here. So I am going to have mvl sine theta theta dot, because now with the negative sign here, so I'm going to get is a negative sign here. And now I can have my Lagrange equations of motion. So this is d dt of delta L by delta theta dot minus delta L by delta theta is going to be 0. So I put this into, this is ml square theta double dot, this one, so minus mbl sine theta and theta dot, and this is, here we have, this is minus minus plus, this is mbl sine theta theta dot, and this is plus mgl sine theta equal to 0. So you see these two are equal, so we are getting rid of these two equations, and what I have is ml square theta double dot plus mgl sine theta is equal to 0. Or you see, I'm going to get the same equation because I get rid of this and divided by this L square. So what I'm going to get is theta double dot plus G by L sine theta equal to 0, or under small angle approximation, this is theta 2 plus G by L theta is going to be 0. So this is under small angle, or a small angle approximation. Okay, this becomes, so now you see again you get the differential equation of simple harmonic motion for this system in which the attachment of this simple pendulum is moving with the constant velocity. So this motion could be anything, like it is moving with a constant velocity. If it can move with have some horizontal motion with periodic motion. So it could be have this is velocity with sine omega t cos omega t. It is doing a simple harmonic motion, and then pendulum is also oscillating. This could be one exciting problem, and if you want you can do yourself. This is, say, in this problem, if I have a situation like this where this say I have this attachment, which is attachment of the pendulum. This is pendulum, attachment of the pendulum, and this attachment is doing a motion, so simple harmonic motion, which is given by this x equal to, say, a sine omega t. Okay, so now you can this is your theta, and this is your this is, say, the L. So this is L sine theta, and then this is your L cos theta. This is your M, and you have x and y. So now you can write the Lagrangian as for this motion also. Now the thing will change, that x, if you define x, is because now this will come into play, because this is the position of this attachment will decide by this. So if the position of this attachment is x0 and y0, so y0 again here is 0, y0 is 0 because this is at reference point on the x-axis, but the x0 is not 0. So you are going to have x0 plus this L sine theta, but x0 here is, say, L sine theta plus x, this is going to be a sine omega t. Okay, and then you can find x dot is going to be L cos theta dot plus this is going to be a omega cos omega t, and this y dot because y is nothing, same, y is same, minus L cos theta, because only y, there is no change in y, so y dot is L sine theta dot, and then you can write your kinetic energy as half m x dot square plus y dot square, and the potential energy is same, is minus mgl cos theta. So once you have your kinetic energy and the potential energy, you can write your Lagrangian, and because the generalized coordinate only is one generalized coordinate is there, so you can one generalized coordinate, this is q1 is only theta, so you have only one equation of motion, that is going to be dt of delta L by delta theta dot minus delta Ly delta theta, and it is going to be 0. So now based on this Lagrangian, you can find out x dot square and y dot square, and this v is there. You can find this equation, and I'm giving you the final equation. You try yourself and try to get this equation. I'm giving you the equations of motions. Equations of motions. So try yourself to calculate it. Try yourself it. So this is I can give you the final equation of motion, that is in terms of theta. This is going to be theta double dot minus a omega square divided by L. This is going to be cos theta and cos omega t plus g by L sin theta is equal to 0. So this equation of motion you can try yourself. So let me write the kinetic energy also for you. This is the kinetic energy. If you remember, this will come out to be half m. Okay, you try yourself. Okay, and then you try to verify this. If you don't get this, try to email me, and then I'll try to cover itself. Okay, so this would be interesting, that you'll get where to differentiate, where to integrate, and then I want you to try this equation. Okay, so there may be another problem based on the simple pendulum, where this attachment of the pendulum could be anything or other. So we will do 1, 2 or 3 more problems in our next lecture. The one basic is like a double pendulum, which I will do. That is complicated and lengthy, but to see that, you have to be very careful when you are calculating this. You have to be very systematic. So if you skip one bit, like while differentiating with respect to time, differentiating with respect to theta or x, if you do a bit of mistake, then it will go till your equations of motion. So as you can see that in my last lecture, I just put a wrong value in d dt of, and then I get equations of motion that's going to be unphysical or physical, but that is not going to be correct way. So you have to be very careful when you are calculating or writing kinetic energy and potential energy. Have to be about potential energy, have to be careful where you have fixed your reference point. So it has to be positive or it has to be negative. Then while calculating the partial differential, you have to be also very careful, because there you get which particular variable is constant or which is not constant with respect to which you are calculating. Also these things have to be you have to be very careful, otherwise you are not going to get your equations of motions correctly. So I think next lecture I'll do a new problem, which the first problem I will do in the next lecture will be a double pendulum, and then I will try to do one more problem that is like a spherical pendulum. So that will give you certain idea. So I hopefully in my next two lecture I'll do certain problems, and I'll move to some different topics. So with this, I think thank you all for concentrating and keeping patience. But keep on doing the problems. Unless until you do calculate your problems by your hand, you're not going to learn. You're not going to have the experience to solve how to attack the problem. So with this comment, I thank you all very much. Thank you.